In the last chapter, I really mean chapter, not section, we looked at power series, sums, these infinite polynomials, so the sums go out infinitely far. In the last section, we looked carefully at sequences of real numbers, and what we want to do in this section is look more carefully and more detail at series of real numbers so that we can justify a lot of the things that we did with power series earlier. I'll say it again, as I said before the last section, that in a sense you can view this section and the next two as the technical details underlying a lot of the stuff we said about power series. All right, so what is an infinite series? We've defined this, but let me define it again. So suppose you've got you have a sequence. And then in this context, these are always called terms, a sequence of terms, bk, where k is greater than or equal to some initial value m. I should warn you of an important thing. It's a mistake that people make all the time, and I probably misspeak myself from time to time. Sequences and series both start with SE, and I think that's the source of this confusion. A sequence is just a list of numbers that doesn't stop. It's just, there's a first thing in the sequence, a second thing, third thing, fourth thing. A sequence is just a list of numbers. A series is what you get when you add up a sequence of terms. They're very different, and it's true that really for every series there are two sequences involved, and I'll get to that in a minute, but it is important for you to try to keep these straight. A sequence is just a list of numbers, and a series is a sum. All right, suppose you have a sequence of terms. Then partial sums S sub n, these form a new sequence. So where you add up the bk's starting at m and going to n. So the partial sums. So this means for then partial sums for n greater than or equal to m. So the partial sums are a new sequence. Right? For each n greater than or equal to m, you sum the bk's. Understand, we're trying to make sense of an infinite sum. And so we form this new sequence. There's a sequence of terms, but the sequence of partial sums. This is where you, as n gets bigger, you add more and more of the terms. And what you want the infinite sum to mean is what this approaches as n approaches infinity. So then we say that the infinite series the sum as k goes from m to infinity of bk converges to some limit L and simply write we simply write inequality if and only if the limit as n goes to infinity of the partial sums, which I'll write it out just so it looks very clear, I hope. Right? We say the infinite sum exists or converges and what it converges to is L, if and only if the limit of the partial sums, so as n goes to infinity, the limit of these sums of the BKs approaches L. We've talked about this before, and it's supposed to seem intuitively obvious. What's a little sad is that people forget or don't think very carefully, and they confuse the limit of the BKs, the things you're adding, with the limit of the partial sums. Those are very different. The BKs are the things you're adding together, and the partial sums are actually the sums whose limit you want to know exists, the sum of the BKs. So try to keep those straight. It's a big mistake that people make. Of course, we say if a series does not converge to something, we say it diverges. And so right now your question should be, okay, for what series can you decide convergence and divergence and what the series converges to or diverges? Or can you tell whether a series diverges and if it converges, what it converges to? And it's I don't know, it's kind of interesting. For many, many series, we can tell whether they converge or diverge, but when they converge, we have theorems that tell us that they do converge, but actually calculating what they converge to in some nice form is either difficult or impossible or unknown how to do. But there are two kinds of series for which we can easily decide convergence or divergence, and when they converge, we can decide what they converge to. They are fundamental. So I want to look at two kinds of series. There are geometric series, which we've looked at before, but I'll remind you what they are. Geometric series, and they're usually referred to as telescoping series. You would think after you've said geometric that you should say telescopic. Strangely, nobody says that, so I'll say telescoping. But yeah, geometric series and telescoping series. These are the most manageable ones for us, but most series are not of this form. But let's look at these. So I remind you what a geometric series is. So let's look at geometric series first. Geometric series are series of this form. The sum as k goes from 0 to infinity of a r to the k. So that is, so when k is 0, you just start at a. And then when k is 1, you get plus a times r. And then each time you raise the power of r. And so on. This is a geometric series. The nth partial sum, or the partial sum out to the r to the n term, would be the sum as k goes from 0 to n of ark. It would stop at r to the n. And it's easy to develop a formula for this. You may or may not remember how we did it. You multiply this by r, see how it shifts things and what's left out. And you can write an equation and solve for Sn explicitly. This is a times 1 minus r to the n plus 1 over 1 minus r, provided r is not 1. And so what do you find? You find quickly that if a is 0, that's a very stupid series, so we're going to assume a is not 0. And you have to deal with the case where r is 1 separately, but, you know, assuming a, so if a is unequal to 0, then the geometric series converges, if and only if. The absolute value of r is less than 1. I.e., if r is between -1 and 1. And what it converges to, and when it converges. It's easy to say what it converges to. If the absolute value of r is less than 1, as you raise to a larger and larger power, as n goes to infinity, you take something with absolute value less than 1, raise it to bigger and bigger powers, it gets smaller and smaller in absolute value. This approaches 0, and you're left with a times 1 over 1 minus r. So what you're left with is, in the case where r has absolute value less than 1, this infinite sum converges to a over 1 minus r. Okay, so these are geometric series. They are absolutely fundamental. In fact, a lot of other series that we know converge, we know that they converge because we kind of compare them with geometric series. Okay, so let's, I don't know, just it's a fun example to look at geometric series that sort of occur in the real world. Almost are real world examples. They're kind of idealized, fun math examples. So a favorite for geometric series that sort of occurs is you're at a restaurant with some other people, and there's like the last piece of bread left in the middle of the table, and nobody wants to take the entire last piece of bread because that seems greedy. And so everybody, everybody tries to take a piece of the remaining bread. So one person takes some, and then the other person doesn't want to take all of that, and the next person doesn't want to take all of that. It gets a little silly after a while. I don't know if you've ever been in this situation, but let's assume there's one piece of bread, and each person, maybe some people start over, each person in succession it looks like in succession takes 1/3 of the remaining bread. Takes 1/3, not even a half. They don't want to be that greedy. 1/3 of the remaining bread. Suppose this goes on forever. Now, of course, this can't go on forever. It would take an infinite amount of time, and eventually, if you keep taking 1/3 of the thing, eventually you'll get down to the atomic level and split an atom, and the restaurant will blow up. But, let's pretend that ideally, suppose this goes on forever. All right. What I want to do is keep track of the total amount of bread taken and the amount of bread remaining. Now, it should be clear kind of physically that in the limit, all the bread goes away. And eventually, you keep getting closer and closer to having no bread. And in the limit, you should suspect that the total amount taken adds up to one piece. So I'm doing everything as fractions of this one piece. But let's see that you get a geometric series. So let me keep track of the bread taken and the bread remaining. So the bread taken and the bread remaining. So as fractions of the initial one piece. Okay, so after the first person takes bread, the bread taken, 1/3 of the initial piece, which is how we're going to keep track of everything. And of course, amount of bread remaining, 2/3. What does the next person take? That person takes 1/3 of the remaining bread, but that is 2/3 of the initial piece, so they take 1/3 of 2/3. What do they leave? They leave 2/3 of this 2/3, so they leave 2/3 squared of the initial bread. All right, how much does the next person take? 1/3 of this remaining 2/3 squared, so they take 1/3 of 2/3 squared. Okay, and what do they leave? 2/3 of this. Well, that's 2/3 cubed. And this keeps going. Each time, the next person takes 1/3 of 2/3 raised to a higher power. All right. So I'm just going to, in the end, of course, the bread remaining, you get 2/3 to the n as n goes to infinity. Well, 2/3 has absolute value less than 1. As n goes to infinity, this thing will approach 0. Good, good. The bread remaining should approach 0. So that means that the bread taken better add up to 1, but let's see that our formula is right. So this is a geometric series. The r here, the r is the thing you multiply by to go from one term to the next. Right? I wrote my geometric series like this. No, I didn't. I wrote my geometric series like this. So r is what's being raised to a power. It means r is the thing you multiply each term by to get to the next term. So if you saw this, and it's not written in summation notation, how do I recognize it as a geometric series? Well, it's just that you go from each term, each summand, to the next one by multiplying by the same thing each time. To go from there to there, you multiply by 2/3. To go from there to there, you multiply by 2/3. To go from here to here, you multiply by 2/3. This is how you recognize the r in a geometric series, or that it is a geometric series, and that's r. It's geometric if you go from one term to the next by multiplying by the same thing each time. Then that thing is what we called r in this formula, and because k starts at 0, the initial term is 1/3. So what you should see is this series, you should look at this and immediately see that it's geometric. The r is 2/3, and a, the initial term, is 1/3. Then what we know is that because the absolute value of r is less than 1, right, this is between -1 and 1, that this series converges, and what it converges to is a over 1 minus r, so 1/3 over 1 minus 2/3. Well, that's 1/3. This is 1/3. Yes, that quotient is 1. Good. Good. Math works again. We were supposed to get 1. We were supposed to end up in the limit. You're supposed to take all the bread. All right. So that's an example of how geometric series come up in the real world. I want to look at a few more things about geometric series. So I'm skipping real world problems. Let's look at the sum as k goes from 0 to infinity of 1.1 to the k, and kind of compare that, or contrast it, with the sum as k goes from 0 to infinity of 100 to the times 0.9 to the k. I think those are the ones that I want. Yes. Okay. This starts out when k is 0, this is 1. When k is 1, it's 1.1. Then when k is 2, it's 1.1 squared. This starts out small. This, on the other hand, when k is 0, this starts out at 100. And when k is 1, it's 90. And so this starts out relatively big compared to this. And you might think, oh, okay, well, then this one diverges and this one converges. No, The theorem tells us quickly, this is geometric, the r is 1.1. This is geometric, the r is 0.9. The fact that a is 100 here, the a in the formula would be 100 here and would be 1 here, is irrelevant to the convergence of the series, unless a is 0, and then it's a very stupid series. It's all zeros. But it's irrelevant that this is big as far as convergence and divergence goes. This converges. Right? The theorem tells us quickly, 0.9 has absolute value less than 1. 1.1 has absolute value greater than 1. You should be able to tell immediately. This one diverges. It's a geometric series where the r is greater than 1. And this one converges. And what this one converges to is easy. It equals the a, the initial term, over 1 minus r. So this is 1/10. It converges to 1,000. Right. So, what do you do, or what else do I want to look at? Well, what do you do if k doesn't start at 0? Maybe that's a problem. So suppose k starts at 2. And you take 100 times 0.9 to the k. Well, this doesn't fit into our formula. Our formula starts at k equals 0. What do? Well, there are a couple of options for what you can do. So let me discuss them both. So this series is still geometric. It's just, it doesn't start at 0, at least with this indexing. One of the things you can do is change the index. So when k is 2, this gives you 100 times 0.9 squared. Then there's 100 times 0.9 cubed plus 100 times 0.9 to the 4th, and so on. Well, this is clearly geometric. You still go from one term to the next by multiplying by 0.9. It's just that the initial term isn't 100. It's 100 times 0.9 squared. So you can write this as a geometric series. I'm going to switch what I call the index, so it won't get confused with this sum. But let's just say the sum is j goes from 0 to infinity of what? Well, you put the initial term, the 100 times 0.9 squared. Yeah, that's 81, but I'm going to leave it as 100 times 0.9 squared. The initial term, and then the 0.9 to the j. This is the same series. It may not look the same because we changed indices. This one started at 2. This one starts at 0. And so that makes things look different. But if you write out the terms, you see that this is the same as, or this is the same as this, and this is the same as this. So, now, I mean, you didn't have to write this to identify A as this, and R is still 0.9. So the series converges, and what it converges to is 100 times 0.9 squared over 1 minus 0.9. This changing of indices comes up fairly often in dealing with infinite series. So let me say, if you didn't write it out and look at it and kind of redo the indexing, what could you do? So you would have the sum as k goes from 2 to infinity of 100 times 0.9 to the k. And you would say, oh, I'd like my index to start at 0. So you'd like an index. You're going to let j, and without writing out any summation, you say, oh, how about if I let j be k minus 2? and I write things in terms, so this means k is j plus 2, and I write things in terms of j instead of k. Well, what do you get? Well, k started at 2. That means j starts at 2 minus 2. J starts at 0. K goes to infinity, so j goes to infinity minus 2. That's still infinity. You get 100, and you get 0.9 to the k, but in terms of j, k is j plus 2. So you write this. But then you can split off a 0.9 squared right here and write this as the sum, as j goes from 0 to infinity, of 100 times 0.9 squared times 0.9 to the j, which is what we wrote before after writing out the terms and going, oh, yeah, it's the same as this. This is how you switch indices in summations. You let something else be your previous index plus or minus something, and then you see how you rewrite everything in terms of your new index j. By the way, I should say that j is a dummy variable. It doesn't matter what you call this. We could have said m equals 0 and m, put an m there, or p equals 0 and put a p there, or giraffe equals 0 and put a giraffe there. It doesn't really matter what you call this index, and you could call it k again, but it's a little difficult to call it k in the intermediate steps, because then you have, let k be k minus 2. So it gets a little confusing when you're substituting. But at the end, when you've rewritten it, you can call your indexing variable k again if you so desire. It would certainly cause confusion in the intermediate steps, though. How else could you deal with that sum if you didn't want to reindex? So we had the sum as k goes from 2 to infinity of 100 times 0.9 to the k. Well, you could say it does start at 0. We just left off the degree, the terms corresponding to k equals 0 and k equals 1. So what you could do is take the sum as k goes from 0 to infinity of 100 times 0.9 to the k and subtract the missing terms. So this adds 2 terms that we don't have. Right? So we need to, that we didn't have over here. So we need to subtract them. So when k is 0, we get 100, which we didn't have. And when k is 1, we get 100 times 0.9, so 90, which we didn't have. So we subtract those. And this infinite sum with these added will be the same as this, because all we did is this sticks on 2 extra initial terms that weren't present, but then we subtracted them. So this will give you the same thing. And so what you should see is whether you do it the way we did it before or do it the way we're doing it now, you get the same thing, that this converges. And what it converges to is 100, the a over 1 minus, now that it starts at 0, it's a over 1 minus r. So this, and you should check that both answers, both ways of doing this give you the same thing. Right. It's worth noting, one of the things I just said here, it's kind of important. I said, okay, yeah, you take this infinite sum, and yeah, this infinite sum is the same as that one, except the first 2 terms are missing, so we subtract those. Well, yeah, that's legal. And it doesn't even sound like much of a theorem. It's so obvious. But the theorem is that if you change a sum, an infinite sum, by leaving off some finite number of terms at the beginning, then this one converges if and only if that one converges. And what they converge to, what the 2 series converge to, differs by the missing terms. I know this sounds completely obvious, and I shouldn't go on about it because that'll only make it more confusing. But all I'm saying is this kind of thing is legal, that if you leave off some initial number of terms from a series, that doesn't affect whether the series converges or diverges. In the convergent case, it changes the total sum by the amount of terms you've left off, but that's it. So that, in fact, what it means is that sometimes when we only care about convergence or divergence, we don't bother saying where the index starts. Like, does this series converge or diverge? Well, we always know we're going out to infinity when we're talking about infinite series, so why bother writing that? And because you can leave off the first finite number of terms and it doesn't determine or affect whether the series converges or not, we typically don't, or we frequently don't bother saying where the series starts either. Although you do need to assume it starts someplace big enough that your terms are defined. So for instance, you wouldn't want to start this one. You wouldn't want to go, oh yeah, the sum as k goes from -2 to infinity, because that would include where k hits 0 and this would be undefined. But if you write something like this, you mean, oh yeah, and I'm starting my k's at 1 or bigger. Like maybe I'm starting at k equals 37 and want to know if that converges. That'll converge if and only if when I start at k equals 1, the series converges. So I'm just saying, sometimes you'll see the summation indices left off because you always know you're going to infinity, and where you start doesn't affect whether the series converges or diverges, provided you start someplace where all the terms are defined. Okay. Before I do telescoping series, there's one other cool thing that this may make you think of that I'd like to talk about. It's geometric series do come up over and over again, kind of in some pseudo real-world applications, but also in a lot of mathematical applications. You may or may not have heard before that how repeating decimal expansions work. And probably the most bizarre one, and hopefully you've heard this before, is that 0.9 repeating, so where the 9s never stop, equals 1. Now, if you've never seen this before, you should think, what? And how is that possible? And the reason it's possible, because you'd like to say, no, these are touching real numbers. This is the next real number just below 1. Well, there is no next real number below 1, because you could always take like half the distance between them and add that. So there is no next real number below 1, and this clearly gets arbitrarily close to 1, so it better be 1. What does this have to do with geometric series? Well, you think about it. What does 0.9 repeating mean? It means, well, that 9 right there means 9/10. And that 9 right there means 9/100. And that 9 right there means 9,000. And this just keeps going. And that infinite decimal, that 0.9 repeating, means that you take the limit. So you do take this infinite sum. You sum this series. But this is geometric. Right? This is a geometric series where you go from each term to the next by multiplying by 1/10. And the initial term is 9/10. And so 1/10 has absolute value less than 1. So this series converges. And what it converges to is 9/10 over 1 minus 1/10. But this is 9/10 over 9/10, 1. So this is why 0.9 repeating is 1, because 0.9 repeating means this infinite sum, which is a limit of the partial sums. And if this bothers you, just what's going on is the 9s, you're thinking they never stop. But it never reaches 1. Right, it never reaches 1. For any finite place, you stop the 9s. But the infinite, saying they go on forever, means you're taking this limit as n goes to infinity. And so, yeah, while it never reaches 1, the limit, if you think of putting in more and more 9s, is exactly 1. All right, that's what geometric series have to do with repeating decimal expansions. Okay, I want to look at telescoping sums now. Telescoping series. So kind of the other case where we can actually find formulas for the sums. Telescoping series, in a sense, every series is a telescoping series, but in another sense, essentially no series are telescoping series. What am I babbling about? So let me give an example. It's the easiest thing to do. So telescoping series. An example, suppose you take the series, sum is k goes from 2 to infinity. The exact one I want is 1 over k minus 1 minus 1 over k. Suppose you take a series that looks like this. What do I mean looks like this? That'll become clear as we go on. But, okay, let's look at the partial sums. So S2, so I'm going to look at the sum is k goes from 2 to n, where n is greater than or equal to 2. I'm going to look at this S sub n. We can actually find a nice formula for the partial sums, which will make it easy to figure out whether this series converges or not, and if it converges, what it converges to. So what happens? You put in k equals 2, and you get 1 over 1. So you get 1 minus a half. Great. And you add to that what you get when k is 3. That's a half minus a third. And you add to that what you get when k is 4. And that's a third minus a fourth. And then you add to that, I'm going to stop in a second, what you get when k is 5, which is a fourth minus a fifth, and so on, out to the last term, which is 1 over n minus 1 minus 1 over n. Okay. Well, let me write the term that comes before this final one. When k is n minus 1, you would get 1 over n minus 2 minus 1 over n minus 1. And then the last term, when k is n, you would get the 1 over n minus 1 minus 1 over n. All right. What do you get when you add all of those? Well, if you look and you think about it for a second, you'll see there's minus a half and plus a half. Well, those cancel. There's minus a third, there's plus a third. Those cancel. There's minus a fourth, there's plus a fourth. Those cancel. And everything keeps canceling. Nothing cancels this first one. And you keep going, and you see that, okay, the minus 1 over n minus 1, that'll cancel with the plus 1 over n minus 1. Everything in between will cancel. This will cancel with something before it. The minus 1/5 will cancel with something after it. Everything will cancel except the initial 1 and the final minus 1 over n. And so what you find is the nth partial sum is 1 minus 1 over n. This is called telescoping because it's like one of those telescopes that collapses and you can extend it like this. I don't know if you've ever seen one. But, you know, this is the telescope collapsed and this is it, kind of expanded outward. So it's easy to get a formula for the partial sums because all these terms cancel, pieces of the terms cancel in pairs. And all you're left with is this first part, the 1, and that minus 1 over n. Well, then what do the partial sums do? Right, the limit as n goes to infinity, the partial sums, which is the sum of the series. This part goes to 0. And so it's 1. Yes, the series converges, and what it converges to is 1. This is an example of a telescoping series where you've got a difference of some function. So you may not remember, but a long time ago, before we did the definition of the definite integral, we had this notation for the difference of a function, the finite difference of a function. And this notation, that delta f done to k, meant f of k minus f of k minus 1. So in this example, where we've got 1 over k minus 1 minus 1 over k, let me write this as, well, I'll write it as negative 1 over k minus negative 1 over k minus 1. These are clearly the same. Minus minus is plus. But it makes it clear that if we let f of k be negative 1 over k, then this is delta of that. So this is delta of the function negative 1 over k. You take this function evaluated at k, and you subtract its value at k minus 1. So, and the reason that series telescopes is because the thing that we're adding is of the form delta f of k. So that when you add, what you get is you get delta f at when k is m. You get delta f at m plus 1. You get delta f at m plus 2, and this keeps going. You get plus delta f. Let me do the partial sums. Let's go out to the nth term. You get delta f, sub n minus 1, and then plus delta f sub n. What do you get? Delta f of m is f of m minus f of m minus 1 plus, so I'm doing the general case now, you get f of m plus 1 minus f of m, and then plus, and this just keeps going, f of m plus 2 minus f of m plus 1. And it goes out to f of n minus f of n minus 1. And what happens is you get cancellation in pairs, but now that I wrote it as delta f and of minus 1 over k, it looks a little backwards from what we had a minute ago. But here's f of m. It cancels with minus f of m, or things aren't right next to each other. Here's f of m plus 1. It cancels with minus f of m plus 1. And things keep canceling in pairs again, except this initial minus f of m minus 1 and this final f of n. And so what you'll get is that this is fn minus f of m minus 1. Right? And the fact that we can write a formula for the partial sums in a telescoping series means that you take the limit of this as n goes to infinity, and you can tell whether it exists or not if f is manageable. So what's the actual definition of a telescoping series? Well, it's a series that you can write in this form where there's a clear f that you've got delta of. So you don't need to worry too much about a technical definition. You should know a telescoping series. When you see one, you've got a term and another term, and they're subtracted from each other, and one of them is just the other one with the k replaced by k minus 1. It should look like that. The reason it's hard to define a telescoping series in a rigorous way is if you actually let these things be the partial sums, so the f that you're looking at delta of, every series telescopes if you don't care how ugly the function is that you're putting here and subtracting. So, right, to be a telescoping series and to be anything we're interested in, it has to clearly be written this way with some nice elementary function that you've got added or subtracted. Well, you need one thing minus another one, where one of them has the k in it and one of them has the k replaced by k minus 1. And then things cancel in pairs. You don't need to memorize the formula I just wrote. It's just look at it. Things cancel in pairs. In the partial sums, you just get the first thing that doesn't cancel and the last thing that doesn't cancel, and you take the limit. So that's a telescoping sum. So when I say in a sense everything is one of these, that's because if you make the functions you're subtracting the partial sum functions, then, and I'm going to make that more clear in a second, everything telescopes. But on the other hand, if you really mean it has to clearly look like some nice function with the same function subtracted from it, but with a k-1 jammed in, then almost no series look like that. It's there's another issue about how you define a telescoping series. Suppose we agree that we're going to call this a telescoping series. Well, I'm telling you we do call it a telescoping series, but you could get a common denominator here and write this in a very different form. So you take 1 over k-1 minus 1 over k, common denominator, k times k-1, so you multiply this by a k in the numerator and denominator. Multiply this by a k-1 in the numerator and denominator. And then you subtract the numerators, the k's cancel, and the minus minus, you get plus. You get plus 1 over k-1 times k. So these are the same series. The terms are exactly the same. We've just done some algebra to write them in a different looking way. I would be hesitant to call this one telescoping, even though, and you can see the problem with the definition, even though this term exactly equals this term, the fact that you've discarded its telescoping nature makes it difficult to want to call this one telescoping, because if you look at it, there's no longer anything to cancel in pairs, because it was split up for you in a nice way in the beginning, and now it's not. So for instance, when k is 2, you get 1 over 1 times 2. When k is 3, you get 1 over 2 times 3. When k is 4, you get 1 over 3 times 4. Well, it's no longer in any way, shape, or form clear that in the partial sums things cancel in pairs and that this thing sums up to 1. It's true, because we proved it writing things in this form, but I would not refer to this as a telescoping series. I would say a telescoping series refers to writing the terms in a way where they're clearly the difference function of some nice function f, like here, minus 1 over k. All right, so those are telescoping series. There's not a big deal to memorize here. It's just if you've got something that's in this form, you just write out the partial sums. You can see the cancellation in pairs. You can see the formula for the partial sums, and then you take the limit. Okay. There's a way that a series can easily diverge, or you can see easily that it diverges. I don't think it's, I guess you can't say it easily diverges. You can see easily that it diverges. So let me take something like the sum as k goes from 1 to infinity of 1. So every term in this series is 1. Don't think, so it converges to 1. No, the terms converge to 1, but every time, when k is 1, you get 1. When k is 2, you get 1. When k is 3, you get 1. You're adding together an infinite number of 1s. Well, of course, that diverges to positive infinity. So it diverges. I'm saying it equals positive infinity, but that's shorthand for saying it gets arbitrarily large, so the limit does not exist. Well, that should be pretty clear. Well, how about if we take something like the sum as k goes from 1 to infinity of 1 minus 1 over k. Okay, now this is tougher. But still, as k gets really big, this part is approaching 0. And so the things you're adding are getting closer and closer to 1. So still, at the end of the day, when k is big, it's like you're adding an infinite number of numbers together that, well, they're all close to 1. They're all less than 1, but they're all close to 1. But they're all bigger. When k is big enough, they're all bigger than a half. In fact, when k is 2 or bigger, all the terms are greater than or equal to a half. Well, then you're adding an infinite number of things that are greater than or equal to a half together. So infinite number of halves would still be infinite. So this is still infinite. And you should kind of think of it as, yeah, it's because it's like adding together an infinite number of ones when k is big, but really it's, okay, yeah, you're adding together a bunch of things that are bigger than like a half or bigger than pretty anything less than 1. So yeah, this goes to infinity for the same reason. And so maybe it's clear, but it probably shouldn't be, that if the terms do not approach 0, so if the limit as k approaches infinity, so this is a theorem, if the limit as k approaches infinity of bk is unequal to 0, then the series that you get by adding the bk's diverges. This is called the term test for divergence. The only conclusion you can ever draw from it is that a series diverges. It can never tell you that a series converges for divergence. If the limit of the terms is not 0, then the sum has to diverge. I need to explain why this is true. You might think these examples make it clear, and they do in some cases. If the limit of bk exists and equals something that's not 0, like a half, then yeah, this is like adding an infinite number of halves together, and of course it diverges to positive infinity in that case. But this limit doesn't even have to exist. I mean, yeah, if it exists and isn't 0, then you should think of this infinite sum as adding together an infinite number of these non-zero, whatever that non-zero limit is. And so of course the series diverges. But this limit doesn't even have to exist. For instance, bk could be -1 to the k, and still the series diverges. But yeah, a nice way to remember this is, yeah, of course, if the terms approach something that's not 0, then this is like adding up an infinite number of those, and this would be positive or negative infinity. So that is kind of a nice way to remember it. But it applies more generally, even if the limit of the terms doesn't exist. So not 0, including if this limit doesn't exist, then it's not 0. So this still applies. It's actually very easy to see that this is true. Logically, this statement is the same as the contrapositive, which is actually the easier way to prove it. The contrapositive is, if not this, then not this. So this is the same statement as saying, if it's not the case that this diverges, so that means it converges, if the sum as k goes from m to infinity of bk converges, then the limit as k approaches infinity of bk has to be 0. Right. These are the same statements. But what's not true, and what people confuse with this, and I'll warn you, and I'll warn you again in a minute, this does not say that if the limit of the terms is 0, then the series converges. That is not true. You cannot conclude just from the fact that the terms approach 0 that the series converges. The terms have to approach 0 fast enough so that adding them up doesn't give you something too big. All right, why is this true? It's actually very easy. Suppose the series converges. Exactly what that means is that if you let Sn be the sum as k goes from m to n of bk, that the limit as n goes to infinity of Sn equals some limit L. So for some L, it converges to L. But, and here's the cool thing, if you look at Sn minus 1, and now to have this be defined, I would need for n to be greater than or equal to m plus 1. What is this? You add up all the terms, including the nth one. Here you add up all the terms to the n minus first one. But then you subtract. Well, that cancels all the sum except that nth term. So Sn minus 1 is Bn. All right, what is that? Who cares? We care. Because the limit, as n approaches infinity of B sub n, and the index doesn't matter. You can switch to k's in the end, which is what will be here. This is the limit as n approaches infinity of, well, Bn. You add up, the terms up to the nth one, but then you subtract all the things you added up to n minus 1, so that just leaves you with the nth one. But remember, if the limit of two things exists, then the limit of their difference exists and is the difference of the limits. So because we're assuming the limit of the Sn's exists and is L, as n goes to infinity, this limit exists and is L. This limit, as n goes to infinity and minus 1 goes to infinity, that exists and equals L, and they're subtracted, and what you end up with is L minus L, which is 0. So the limit, assuming that this limit exists, the limit of the Bn's has to exist and be 0, because you can write Bn as the difference of the nth and the nth minus first partial sums. All right, this is the term test for divergence. So it can quickly tell you that things diverge. If the series diverge. If the terms of the series are not approaching 0, then the series diverges. So, this diverges. And by the term test for divergence, right? The terms here are not approaching 0. They're not approaching anything. As n goes to infinity, this oscillates. This goes minus 1 plus 1, minus 1 plus 1, minus 1 plus 1. It doesn't approach anything. In particular, the limit is not 0. The limit doesn't exist. So this diverges by the term test for divergence. The term test is probably the easiest way to conclude. Somebody hands you a series and tells you, okay, show that this series diverges. The term test is the easiest way you could show it diverges. But if the terms approach 0, the series could still converge or diverge. You have to do more work. So I want you to remember, we've talked about the harmonic series and the alternating harmonic series. So let me put these back up. We've looked at both of these before. So this is the harmonic series. It goes 1 plus 1/2 plus 1/3 plus 1/4 plus 1/5 and so on. This is the alternating harmonic series. It does exactly the same thing, but every other time you have a minus sign. The alternating harmonic series. And so this one goes 1 minus 1/2 plus 1/3 minus 1/4 plus 1/5 minus 1/6 and so on. We've talked about both of these before. This one converges. We proved this. We proved this by looking at the Maclaurin series for the natural log of 1 plus x and proving that the remainder term went to 0 even when x was 1, so that the Maclaurin series equaled the natural log of 1 plus x at 1. So in fact, we know this converges, and what it converges to is the natural log of 2. We proved that. said before that the harmonic series diverges. I haven't proved this for you. I'm about to, but I haven't proved this for you before. The terms here are almost the same. It's just that this alternates, plus or minus 1. So the terms here are approaching 0, and the series converges. Great. But understand what the harmonic series is an important example of. This is extremely important, and it's probably the most important example of this. The terms, the most basic one, the terms here approach 0. As k goes to infinity, 1 over k goes to 0. The terms are definitely approaching 0. The series still diverges. The fact that the terms approach 0 is not enough to guarantee convergence of a series. You're adding more and more terms together. So a minimal necessary condition for convergence is that the terms approach 0. But if the terms don't approach 0 fast enough, they don't kind of compensate for the fact that you're adding more and more of the terms together, and the sum can still get arbitrarily big. So this is extremely important, and we try to beat into students over and over again that the term test for divergence, you can only conclude that series diverge from it. If the terms do not approach 0, then the series diverges. If the terms do approach 0, you have to do something else to decide what happens. If the terms approach 0, maybe the series converges. If the terms approach 0, maybe the series diverges. And the point is, you just have to do more stuff to figure it out. Okay, let's look at the harmonic series and prove that it diverges. We put this off for a while. I don't even know how many times now I've said that the harmonic series diverges, but it's been a bunch. And I'm going to write the harmonic, a lot of terms of the harmonic series, and there's a reason why I'm writing all of these, and you just have to bear with me for a minute. All right, there are some terms of the harmonic series. And what we'd like to see is that the partial sums are getting arbitrarily large so that this sum diverges to infinity. And to show that, what we need to show is that the partial sums are getting arbitrarily big. If we go out far enough, we can make this sum as big as we want. How do you do that? There aren't nice tricks like we're about to do for every series, or there's no standard trick that works for every series. You group things how I'm grouping them now. So how am I grouping them? I'm always stopping, I'm grouping things, and I'm stopping after the next power of 2. So here's 2, here's 2 squared. Well, you can think of this as 2 to the 0. There's 2, there's 4, there's 2 cubed, there's 2 to the 4th. Okay, so I'm stopping after every power of 2, and I'm starting my grouping after the last power of 2. Why on earth would you do this? Well, it's because this term is the smallest thing in this sum. Right? A third is bigger than a fourth. So this part is greater than a fourth plus a fourth. But that's 2/4, so that's a half. So certainly this part is greater than a half. What about this? All of these terms, 1/5, 1/6, and 1/7, are greater than an eighth. So this is greater than 4 times an eighth. But that's a half. What about this part? All of these terms are greater than 1/16, except for this one. So, but all the other terms are greater than 1/16. How many of them are there? 1, 2, 3, 4, 5, 6, 7, 8. 8. This part is greater than 8 times the 16th. Well, that's a half. So what happens? If you keep grouping, after the previous 1 over power of 2 and group to the end of the next 1 over power of 2, what happens is every single grouping is bigger than a half. So you get 1 plus a half plus something greater than a half plus something greater than a half plus something greater than a half. And you keep adding more and more things together that are greater than a half. Well, then it gets arbitrarily large. Because if you add enough halves, you can get bigger than anything. So this sum is infinite. Because you can make it arbitrarily large because you can see that if you go out far enough, you're greater than any multiple of a half, or any multiple of a half plus 1. So just by going out far enough, you can make the partial sum as big as you want. So the whole point, the harmonic series diverges. Even though the terms approach 0. They just don't do it fast enough to compensate for the fact that you're adding things together, even though the terms approach 0. This is an extremely important example to remember. It is a fundamental mistake that people think if the terms approach 0, then the partial sums converge, so that the series converges. It's just not true in general. All right. I don't have much more to say. I just want to briefly mention the most basic algebraic properties of convergent series. Convergent series behave nicely in many respects. And one of them, and this is left as an exercise because this is easy and just follows from kind of the corresponding properties for the partial sums. Suppose C is a constant that's unequal to 0. Then a series AK, as k goes from m to infinity, converges if and only if the series where you multiply each term by C converges. And when they converge, what I'm about to write shouldn't come as a shock to you. The sum is k goes from m to infinity of c times a to the k equals c times the sum as k goes from m to infinity of a sub k. That is, you should think constants, multiplying by a constant distributes over infinite sums. Right? Of course, multiplying by a constant distributes over partial sums and limits of products or products of limits. That's all there is to proving this. But still, it's nice to know. Multiplying by a constant distributes over even infinite summations. So that's nice. And then there's summing to convergent series, although I'll write things in a slightly more general way. On 2, suppose you have a convergent series. So suppose the sum is k goes from m to infinity of ak converges. Then the sum is k goes from m to infinity of bk converges if and only if the sum as k goes from m to infinity of ak plus bk converges. And when they converge, the sum as k goes from m to infinity of ak plus bk. This isn't going to be a shock. As the sum as k goes from m to infinity of ak plus the sum as k goes from m to infinity of bk. Right? And it's because the partial sums obey this property. But what these two things together say is when you're looking at a linear combination of series, so where you've got the terms here, the terms of this complicated looking series are constant times something you know the sum of plus a constant times something else you know the sum of, that you'll be able to decide whether your complicated series converges or diverges and what it converges or diverges to if you knew that about the other series. So, for instance, just a quick example. We don't have many series that we know the sum of right now. We have telescoping ones and geometric ones and the alternating harmonic series. So let's just, what the sum is, k goes from 0 to infinity of 3 times 1/2 to the k minus 7 times minus 1. Oh, I'm sorry, let's start at 1. Well, I don't, okay, let's start at 1. Minus 7 times minus 1 to the k minus 1 times 1 over k. Suppose, quick, does this series converge or diverge? And if it converges, what does it converge to? Well, you see a difference of two things, which you can think of as multiplying by minus 1 and adding, if you want. So that, well, if you think of this as plus negative that, if we knew that this series converged and that series converged, we would know the whole thing converges. Does this series converge? Yes, it's geometric with r equals 1/2, which has absolute value less than 1, so this series converges. Does this converge? Yes, because it's minus 7 times the alternating harmonic series. And we know the alternating harmonic series converges, so minus 7 times it converges, because it's the c here is minus 7 from the last theorem. So yes, this converges. And what does it converge to? Well, it converges to, we've had the a inside our geometric series before, but the last theorem with the c in it told us we can pull out constants. What this converges to is this. And normally you wouldn't kind of check, you'd kind of check the convergence of this on the fly. You'd write that this should be this, keeping in mind, and I want to say this more carefully in a second, that if these diverge, if this diverges and this diverges, then splitting it like this isn't necessarily correct. But what you're going to do, what is typically done is you split it like this first, and then check whether these converge. And if they converge, you know it's okay. If one of these diverges, you have to go back and start over because this still might converge or diverge. The fact that one of these diverges wouldn't tell you that the original thing diverges, but we'll come to that in a minute. This is 3 times, this is a geometric series. A, where r is 1/2, a is the initial term, which will be what you get when k is 1. It's also 1/2. Oops. So you get 1/2 over 1 minus 1/2. minus 7 times, and then we know that this is the alternating harmonic series. It's the natural log of 2. Half divided by half, that's 1, so we get 3 minus 7 times the natural log of 2. So, right, you can split up sums and differences and pull out constants, provided that the series converge when you're finished. How is it possible that you could split something up? If you have divergent series, you could split it up, get divergent, see that the pieces are divergent, but the original thing is convergent. Actually, that's very easy. It's so easy, it looks incredibly stupid, but it's worth noting that suppose you take this series. All right, I know this looks stupid. 1 over k minus 1 over k. Well, this is 0. You're adding together an infinite number of zeros. This definitely converges to 0, no doubt about it. All the terms are 0. But it should make it clear that you have to be careful when you write things as kind of a sum or difference of divergent series, because this, right, you might think, this must be equal to the sum as k goes from 1 to infinity of 1 over k, plus the sum as k goes from 1 to infinity of minus 1 over k. Well, neither one of these exists. This diverges to positive infinity. This diverges to minus infinity. Aha! Positive infinity minus or plus negative infinity is 0. Well, no, it's not. You can't do arithmetic like that with infinities. If you get some answer that looks like infinity minus infinity, you need to check on how fast they're going to infinity. This time it looks reasonable, but the whole point is, if you split something up and these diverge, you can't conclude that the original thing diverges. It might not. It might go to 0. On the other hand, if one of them converges, then the theorem said, when you split up sums, said that if one of them converges, then the other one converges if and only if the original thing converges. So if this diverges and this converges, it would tell us that this diverges. But that doesn't happen here. All right, there's one last thing I want to say in this section. It's an example of something bizarre that can happen with divergent series, and then a theorem that says, and this doesn't happen for convergent ones. But it's good to notice from time to time that infinite series can do bizarre things. So consider the series (1 minus 1 plus 1 minus 1 plus 1 minus 1 plus 1 minus 1 plus this series. Now, I've written it like this, and I mean that I expect, well, it might be slightly unclear to you what the actual terms are, but they are minus 1 to the k. So when k is 0, you get 1. When k is 1, you get minus 1. So what we really mean here, since we're always talking about summations, is I meant this. This might have made it more clear. Plus 1 plus a minus 1. Put parentheses around all the minus 1s and write plus a negative 1. But that's, most people would have assumed that was what I meant anyway, but maybe I'll write it like that. Okay, so now maybe it's more clear what the terms are, but what's the point right now? The point right now is, okay, great. Normal addition is associative. Associative means that parentheses don't matter. Commutative means the order in which you do things, whether you have one thing before another one or after, doesn't matter. But associativity means A plus B plus C is the same as A plus B plus C, which is why we don't need to bother writing parentheses. We can just write A plus B plus C. Whether you add B and C first and then add A to the sum of B and C, or add C to the sum of A and B, this says it doesn't matter, so we just write this. I'm not saying anything about the order, the fact that you need to keep this in the same order, like how come A plus B plus C is B plus C plus A? Well, that uses commutativity of addition. But associativity is just the parentheses don't matter. Well, here's this infinite sum. This diverges. We know this diverges. By the term test for divergence, the terms do not approach 0. This diverges. In fact, we use the term test, but the partial sums, they go 1, and then you add this term and you get 0, and then you add a 1, and then you add this term and you get 0. The partial sums are going 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0. The partial sums are not approaching a limit. So you don't need to apply the term test if you don't want to. You can actually look at the partial sums and say they're not approaching a limit. They're oscillating back and forth between 0 and 1. Fine. But this series diverges regardless of how you see it. But now I could stick in parentheses here. Suppose I look at the new series I get by grouping terms together. So when it's written out like this, that's just by inserting parentheses. Well, then this is 0, this is 0, this is 0, this is 0. This series converges. And what it converges to is 0, right? So this is kind of scary. Understand what this means, that if you have a divergent series, it may be possible by grouping some of the terms together and looking at the new series you get by considering this group your first term, this group your second term, this group your third term, and so on, to get a convergent series. So inserting parentheses into a divergent sum can make it converge. That's a little scary. The good news is the theorem is if a series converges, then you can't insert parentheses and make it diverge, and you can't insert parentheses and change the sum. Then I'm going to write it as inserting parentheses, so grouping, well, maybe I won't. Then grouping terms together does not affect the sum. It still converges, no matter how you group things, and it converges to the same thing together. It does not affect the sum. Phew. Well, that's good. It is a little scary that sticking parentheses into divergent sums can make them converge, but at least convergent sums behave nicely as far as grouping goes. All right, well, that seemed like a fair amount of material. Actually, it's just introductory. In the next section, we're going to have a bunch of tests for whether series converge or diverge, but we're only going to apply them for reasons that we'll talk about. It's easier to deal with series that don't have both positive and negative terms in them. So we'll fix ourselves at looking at series that have all terms that are greater than or equal to 0. All the same results, analogous results, are true for series where the terms are all less than or equal to 0. It's just you negate the results that we have. But yeah, it's just a kind of a weird fact that non-negative series with non-negative terms, so no negative terms, behave more nicely in lots of respects than series with positive and negative ones. So next time, a lot more stuff, a lot of tests for convergence and divergence of non-negative series.